minus I'm integrating on a set whose measure is 0. Integrating what? A non-negative function. Okay, so this is also a result that when we defined integral, actually we said that this integral can be 0 due to the two reasons actually. If the integrand is 0, or the set on which you are measuring with respect to the measure is 0. Now since the mu of h is 0, so this must be 0. And mu of h is 0 because mu is absolutely continuous with respect to each other. You get it. Okay? Almost done. The last thing that I need to do is to just extend this conclusion to sigma-finite measure. Okay? Extend this conclusion to sigma-finite measure. So now our new view is sigma-finite. Let's do the phase 2. Where mu is a sigma-finite measure. Okay. What do I mean by a sigma-finite measure? This means that there exists a sequence of measurable functions that increase to the set x, okay, such that the measure of all of these fi's is finite. Okay? And by increasing to x means that the increasing sequence and the union is x. That's what I mean. Okay. Now since mu of fi is finite, I don't know, so I want to use the previous conclusion and I know that mu of fi is finite. So let me restrict the mu I and restrict mu to fi and give it a name mu I. Now that is a finite measure. Okay? That's a finite measure because the domain of this is fi. Okay? So it's a finite measure. So I can run the previous conclusion. I can use the previous conclusion. In what sense? Okay. And similarly, define mu I to be the restriction of nu onto the fi. So let's change the underlying space. Let's institute of x, do everything with fi. So I can say that with respect to fi, the previous result is true. Both are finite measures. So just replace the bigger x by what do you say? Fi. Then, okay. Now here's the thing. If you can ask a question actually. I know that nu and mu, the nu is absolutely continuous with respect to mu. One part is missing. Is nu I absolutely continuous with respect to mu I? Because I can't apply afterwards result actually. Is nu I absolutely continuous with respect to mu I? So in order to show that I need to assume, let's take mu I equal to 0. Okay? And I can say that this is same as mu I of A intersection fi. Okay, where A is measurable set under mu I. Okay. This would be the case. Okay. Mu of A intersection fi. Because this is a part of the bigger space. Okay. And now, since this is a set that is 0 under mu, and nu is absolutely continuous with respect to mu, so I would say that the nu of A intersection fi is also 0. Okay? And that simply implies, okay, that nu I of equal to 1, 2, and so on and so forth. All right. You see? It is important. Now, if nu I is absolutely continuous with respect to mu I, and both are finite measure, so by case 1, I can find a measurable and non-negative, measurable Fi which are also non-negative, such that d mu I is f d mu I. Okay, it's just a shortcut notation. In other words, what simply I mean is that nu I of A is equal to the integral of A. So that's just a notation, mimicking notation. Okay? This is the case.
F sub I.
F sub I. Okay? F sub I. F here. The F sub I, yes. Yes, you are right. Okay. By the way, I can also show using a similar kind. So here's the thing. So that's a sequence now. So it's like of measurable function, like F1 and F2 and F3 and so on and so forth. By a similar argument as we gave in the case 1, I can say that Fi would be equal to Fj, okay, on what? Fi for all I less than or equal to j. Do you agree with it? So Fi is defined from where to where? Let me take a difference. Okay. Say F1 minus F2 with respect to which measure?
Bigger 2.
So let's take mu 2. Okay. And this is same as F1 mu2 minus F2
dmu2 is same as dmu1.
So this is same as f dmu1 roughly, and this is same as f2 dmu2. And this guy is what? Oh, so this is kind of your mu of A1, mu1 of A1, right? And this would be mu2 of A2. I can, इसका मतलब ये है कि ये जो set लेना है, I have to take it from a smaller sigma-algebra, not from the bigger algebra. Okay? So the A must be from the smaller sigma-algebra. Okay? And if this is the case, so that I can write here, what do you say, mu2 of A as well. So if A is from the smaller sigma-algebra, then the mu2 of A would be same as mu1 of A. So this must be 0. So we're going to say that on this smaller part, F1 and F2 are agreed at. So that's just the roughest sketch actually of what you want to do. So think about it in a more detailed and precise manner as well. So roughly what I am claiming, okay, is that since each of the nu I is absolutely measurable with respect to the mu I, so there exists such non-negative measurable functions which can be treated as the Radon-Nikodym derivative of nu I with respect to the mu I. Okay? And Fi would be Fj on Fi for all I less than or equal to j. So in other words, if you have F10, want to see the F10 on, say, small f5, it should be same as the f5 actually. Like, that's what essentially it says. Now, define a function. So in other words, using these functions, define a function f. And define function f of x as fi of x if I, okay, so if x is in fi. Take it, define fi of x if x is in fi, right? So in other words, if x is in f1, then f of x is f1 of x, and so on and so forth. Okay? Is it making sense? Is this measurable? Because the function is defined through measurable function, so it must be measurable. And my claim is that this is your required f actually. Okay? Now consider the nu of A intersection fi. Alright? For any A in sigma-algebra A, consider the nu of A intersection fi. So this must be same as nu I of A. Agree? And if it is nu I of A, this would be same as integral of fi d mu
d mu I.
Okay? And this is same as that if I say that this is same as A intersection fi and what you see. Okay? Okay? And now I'm saying take the arbitrary A actually. The arbitrary A, the nu of arbitrary A is A intersection x. Okay? Then x can be broken down to their fi's. So I can write this as the nu of union I equal to 1 to infinity. Okay? Of AI. Okay, A intersection fi. Okay? And this is same as the sum. So nu of A is sum I equal to 1 to infinity. Okay? Nu of A intersection fi, which is same as the integral I equal to 1 to infinity f A intersection fi d nu, and obviously this is same as f d nu here.
Sir, I have trouble with this thing.
Huh?
The union going to the sum.
Why not?
Distracting is.
They. Achha. Okay. Okay. So the other thing that I can do is that put a limit here. Okay. Can I say that this is same as limit n goes to infinity? Okay. Of nu of union of I equal to 1 to n and A intersection fi would point. ठीक है? अब तो कर सकते हैं. Still we reach to the same conclusion. That limit n goes to infinity of sum I equal to 1 to n mu of A intersection fi, and this is same as we put infinity here and you're going to get what? The integral of f A and d. Okay. Please do that. So what does this Radon-Nikodym Theorem is going to, and it's telling us that if you have a sigma-finite measure that is absolutely continuous with respect to a finite measure, then you can always find the Radon-Nikodym derivative. Okay? In such a way that one measure can be written as the integral of the derivative. Right? That's it. So,
Case 2 आप लोग consider case 2 सर